A linear congruence is an equation of the form a times n is congruent to b mod c, where a, b, and c are integers. We can see that if n is a solution, then so is any other integer of the form n plus k times c for any integer k. We should not be surprised by this because we showed in the previous chapter that we can replace any integer with any other one that is congruent to it without breaking the equivalence. So rather than talking about all integers, we will look at a complete residue system. Another way of saying this is that we're going to be looking at sets of solutions whose elements are mutually incongruent to each other. If we look at the equation a times n is congruent to b mod c, we can see that it can be rewritten as an minus b is equal to c times k, which is also expressible as an plus c times negative k is equal to b, where n and k are unknown integers. This is essentially the same as solving ax plus cy equals b, which we've already done except for the transposition of a couple symbols. We know that this equation has a solution whenever the GCD of a and c divides b, and if that's the case, we can use the Euclidean algorithm to find a solution n naught k naught. And once we have that solution, we can also get all the other solutions using theorem 2-4. Using the symbols from our problem, this is what the equations will look like. In fact, by the division algorithm, there are just integers q and r such that t is equal to q times d plus r, where 0 is less than or equal to r less than d. If we plug this into the equation for n, we can focus on the solutions modulo c. By taking r to be the values 0, 1, 2 up through d minus 1, we get all the mutually incongruent solutions. These calculations constitute a proof of the following theorem. Theorem: if d is the GCD of a and c, then the congruence a times n is congruent to b mod c has no solution if d does not divide b, and it has d mutually incongruent solutions if d does divide b. Again, all we've really done here is reframe what we already know about linear Diophantine equations in terms of congruences. In class, we will work with numerical examples and get some practice solving these congruences. We will end this video with a couple definitions and a quick corollary. Definition: we say that a solution n of a congruence is unique modulo c if any solution n prime of it is congruent to n modulo c. This definition is introduced for technical convenience. We know that if we have one solution, then any number congruent to it modulo c is also going to be a solution. We're just using the phrase unique modulo c to say that all the solutions are congruent to this one value modulo c. Definition: if a times a prime is congruent to 1 mod c, we say that a prime is the inverse of a modulo c. This language comes up from algebra. We would technically be saying that a prime is the multiplicative inverse of a modulo c. Corollary: if the GCD of a and c is 1, then a has an inverse and it is unique modulo c. To prove this, we simply note that the GCD of a and c is 1, and so we can apply theorem 5-1 to see that a times n is congruent to 1 modulo c must have a unique solution modulo c. For example, 2 is the inverse of 4 modulo 7 because 4 times 2 is congruent to 1 mod 7. And if you try any other value modulo 7 and multiply it by 4, you will not get 1. If you've taken abstract algebra, this type of statement should feel familiar. If you haven't taken abstract algebra, don't worry about it. We won't be using anything from this course without developing it ourselves first.
Thank you for watching this video. I'm currently dabbling with the idea of creating more videos like these for my classes, and I welcome constructive comments that might help me make better videos in the future.